Hey guys, I'm going to record this short video so that hopefully those of you who are not doing lab can watch it and get some benefit and take notes before you're doing your practice. Also, this is what my face looks like, so now you've seen that. Eighth period, you didn't get to the example of the Springbok, so I'm going to work through that really quickly. The rest of you guys, if you actually want to fast forward about a minute or two, then you can jump in where we'll be picking up kind of on the next part of the notes. But if you want some recap, the Springbok here, if we're given an acceleration, we're given a distance about how far it's accelerating as it's bending its legs and then getting ready to pronk. And of course, there's a video link to that pronk in action in Google Classroom if you're interested. But if we think about it, we could use our third kinematic formula, which looks like this. Because we know the distance, we know the acceleration, we know if it's crouching down and getting ready to jump, that it's starting at a velocity of 0, and it's going to go to some speed as it leaves the ground, which they've indicated they want to know here. So that would tell me that v squared is equal to, this whole thing is 0, plus 2 times the acceleration, 35 meters per second squared, times my height, which is where I'm crouching and then going up, so that a full distance of 0 to 0.7, so 0.7 meters is my displacement. Okay, from here I'm just kind of solving, so v would be equal to the square root of 2 times 35 times 0.7. And I'm dropping units just for the sake of space, which means my takeoff speed is about positive 7.0 meters per second. Now that I know that, I can figure out how high the object goes, in this case the antelope, by figuring out with the third kinematic formula, but with different numbers. So if I now know that this guy is leaping off the ground at 7.0 meters per second, as it goes up into the air, it's going to eventually go to a max height, and then it's going to come back down. But at that maximum height, I know that the velocity is going to be 0 meters per second, at least for a second. So it's taken off at a 7, stops at the highest part, so then that's a new kind of vertical displacement. So if I want to know how high it goes, I can use the same formula, but with different numbers. Instead of my final speed being what I'm solving for, now I'm setting the final speed as 0. So 0 meters per second equals v sub o. Now that is now my takeoff speed that we found in the previous part, 7.0 meters per second squared, plus 2 times, as I'm flying through the air, my acceleration is no longer 35, now it's negative 10, since gravity is the only thing that's acting. And then all of that would be times my height, which is of course what I'm solving for. Rearranging, I would have 7 squared is 49. Subtract that across, so I'd have negative 49 equals negative 20 times delta x, which means that delta x is equal to 49 over 20, which is about positive 2.5 meters. So the Springbok antelope can actually jump close to like 9 to 10 feet. Kind of impressive. Now the rest of us picked up there, and so if we jump to the backside, we're going to then go on and think about a motion diagram. So if we were to draw a motion diagram of a ball just being tossed straight up in the air, the motion would look something like this. It would be launched. We would draw a big long arrow because of course we're throwing it with a high velocity, and then as it rises to the peak, that arrow is going to get shorter and shorter, showing that the velocity is decreasing. Eventually it's going to stop momentarily, then it's going to come back down and it's going to start speeding up in the negative direction. And so that would be our motion diagram. As far as a velocity versus time graph, make sure we label here velocity in meters per second and then time in seconds. If we throw it up in the air, it starts with an initial positive velocity. So we could pick a point maybe right up here. Say this is my initial launch speed, v sub o. And then as it flies up into the air, eventually it's going to stop. Let's just use kind of as much of the graph as possible here. So let's say that it takes, looks like about 10 seconds to get to the high point. Then as it comes back down, of course, we're going to be negative. So if I was to just connect this full thing, it'd be a nice linear trend. Negative constant slope. And if we think about that graph, we can kind of do some interpretation on the questions below. So based on that velocity time graph, which you can see on your paper, what would the slope of this line be? If we think about it being a velocity time graph, I know that the slope should be the acceleration. The area under the line, again, velocity time, so if I think about multiplying velocity times time, and rearranging my velocity as distance over time equation. If I do the area here, which would be velocity times time, that would give me a displacement. Now I know that this shape is a triangle, so I would have to divide that value by 2 to get the actual displacement, but regardless, the area under the curve represents displacement. At which point in the motion of the ball is the acceleration 0? Well, if we look at the line, the entire slope is the same. So therefore, the acceleration is 0, never. The entire acceleration is negative 9.8 meters per second squared, or negative 10, as we use. And then at which point in the ball's motion is the velocity 0? That would be only once. That would be when the velocity versus time graph crosses that x-axis. So when the v versus t graph crosses the x-axis. Some of you are still struggling on these graphs and you're picking with position versus time. When that crosses the x-axis as a velocity of 0, that would be a position of 0. In this case, it wouldn't actually go back to location 0 until the very end of the motion, when all of this negative area matches up with the positive area as it gained and flew up into the air. Then as it comes back down, this would actually be where it hits the ground. E says, what is the ball's initial velocity, the point it leaves the hand, related to the ball's final velocity? If I throw it up and it accelerates for a given amount of time, as it falls back down, it's going to accelerate for the same amount of time. So the answer here would actually be that it's equal in magnitude, but as it's falling down instead of shooting up in the air now, it would be opposite in direction. And so we can apply that theoretically to lots of different problems. In terms of the time, if we think about the time going up and the time coming down, of course, that's also going to be equal. So the time up is equal to the time down. And how does the time it was going up relate to the total time? The total time, t total, would be equal to either 2 times the time up, which is also the same as 2 times the time down, because time up is equal to time down. You could also do your time up plus your time down to get your total time. Any of those different mixtures would work. All right, last but not least, if we have something like a volcano shooting a chunk of rock straight up into the air, this is an actual old AP question. Ignoring air resistance, what is the velocity just before it returns to the surface of the volcano? So we're a volcano, explodes, shoot rock in the air, flies up, comes back down right to the same place, brim of the volcano. If we think about the only force acting upon the rock and air, ignoring air resistance, is gravity, then if it was shot up at 30 meters per second, it's coming down at negative 30 meters per second. That's it. The other example here, if an English teacher uses a potato launcher to shoot a potato straight up in the air, I don't know why they're doing this, but I'm sure it has something to do with The Great Gatsby. The potato goes up and goes straight down into the English teacher's head. And if the total hang time was 9.6 seconds, how long did it take the potato to reach max height? We could do this kinematically and find the velocity and find the acceleration and do all these different things, or we could just think it's going to take half the total flight time to get up there. And so half of 9.6 is, of course, 4.8. And we can be done. You could check that if you wanted to. And that's the last example. Last example here is a baseball player. Let me scooch myself over. Whoa. We have a baseball being thrown straight up in the air, and it hits the ground 5.2 seconds later. And we'll actually go do this lab next week. We're going to go play wiffle ball at the request of some people. So on this one, if we throw the ball straight up in the air, ball go up, and then ball come down, 5.2 seconds equals t total. If I wanted to know the maximum height, am I going to use this total flight time? No, that would make no sense. I'm going to use half of the flight time. So half of that flight time is 2.6 seconds. So t to the halfway point, I can make a note here, is 2.6 seconds. And if I think about at the maximum height, the velocity for just a second is going to go 0. So thinking about that, I can use kinematics to find how fast it left the thrower's hand. So just thinking in my very most basic equation, v equals v sub o plus at. If I know the t, if I know the acceleration, I can find the initial velocity, v sub o, because at the highest point, the velocity goes to 0. So by setting this final velocity as 0, I'm going to set that as 0 at max height. That'd be 0 meters per second, equals my launch speed plus -10 times my time, 2.6 seconds. So obviously we can see that v sub o, if I subtract that across, I would have negative v sub o. I'll show the algebra because I know some of you guys are still a little tricked up on those. Would be equal to -26 meters per second. Notice we have seconds squared canceling with seconds, so leaving me with just meters per second, which means of course v sub o is equal to positive 26 meters per second if we divide both sides by 1. Positive because how did I throw the ball? Up. I'm no baseball player, but I think that's how the sports ball works. Now, you could also find the max height now that we found this initial velocity by using our third equation, but they don't want us to do that, so we're not going to flex like that. Now, the last question I want you to actually try. This is an AP level question where you have 2 cliff jumpers jumping off into a pool of water and also throwing stones vertically downward. So if you think about those different motions, if he throws the rocks downwards and sees that 1 second apart they hit at the same time, you can find out things about each stone. So I'm going to challenge you to do that. When you're done, check your answers on the PDF copy of these notes and see if you got it right. If you didn't, kind of follow along and see where you went wrong. And then you can start practicing on the Big 3 with Freefall practice that's in Google Classroom.